Hi, my name is Dana Golden, and today we're going to finish up our lecture on electricity markets by looking at transmission, which is, my favorite part of the process. I'm biased. This is the type of research I do, but I think it's really great. So what is transmission? Transmission is the process of transporting electricity from generation facilities to distribution systems. So it leaves the generator. It needs to get to your neighborhood. It needs to get to where it's going to be distributed locally, and that's the transmission. It operates generally at higher voltages. This depends on which transmission system you're using, but generally, uh, if you look at V equals IR, which is the prominent electricity formula that governs the relation between voltage, current, and resistance, you want to maintain current because there's a relationship between current and voltage and power. And so you want higher current, and then you want higher voltage, and that will lower resistance. And so you operate at high voltages to transmit over long distances to lower energy losses, and then at the local place, you step it down using a transformer and a converter to distribute over a local distributional network that has lower voltage into your home, which has a still lower voltage. I mean, that's the same voltage as the distributional network if all of it's worked well. But and connects generation plants to consumers via a network of transmission lines and substations. So key components of transmission, you have the transmission lines. So the low voltage traditionally is like 115 to 220 is like a pretty low voltage. And then after there, you get the next standard, which is 230 to 300. And then you have 345 is when you're really getting 345 kilovolts, I should say. I should be giving units, kilovolt. You're getting into like high voltage. And then beyond that, you have 500, 735, and then you can have even higher voltages for very long distance transmission. So transmission lines tend to be high voltage, and these are like examples of like medium voltage compared to like really long distance transmission. And you have alternating current, which is most of it. You have regular alternating current transmission lines, and you have whole high voltage alternating current transmission lines. And then you have direct current transmission lines that transmit a lot of electricity over very long distances. There are no multi-terminal DC lines. There are no grids that are made up of just DC lines for transmission, but there's a lot of work on this. So you have the transmission lines, then you have the substations where you step up transformers to increase the voltage for transmission, then you step down, use the step-down transformer to reduce voltage for distribution. And then you have control centers, or you might have heard of SCADA is a technology used here where you're trying to control electricity generation and distribution. So here you manage grid stability, load balancing, and system reliability, and use real-time monitoring and dispatching systems. It used to be a real events because you had to monitor these real time. So you had someone who lived at the station, the control center, and all the time. Nowadays, you have a bit better quality of life, and you have people who are there all the time, maybe one or two people, but who are working in shifts. They're not living at the station anymore. But normally, most of the work at 2 a.m. is done by software. So challenges in transmission, you have congestion, which is the limited capacity in high demand regions. So congestion is why there's dispersion price across locations, because you have an inability to send generation between two places because of too much generation on one line. And then you have losses. You have an electricity loss due to resistance in lines, which you lose a little bit of energy to heat every time you transport electricity, and this increases with distance. And then you have integration renewables. You have variable generation that requires grid flexibility. You need to have somewhere to send it because it always has to balance, and this can either be done through long-distance transmission or through storage. And then, of course, building transmission is expensive. It's expensive and hard. You have to get permits. You have to do a lot of infrastructure investment. The Biden administration helped with that some with a bipartisan infrastructure act, but there's still a lot to be done. There's a proposal, the Big Wires Act, to encourage more transmission build out, but it's a hard time. There needs to be transmission build out, and it's not happening nearly as fast. I think everyone wants this. It's just, systems are hard to change. But there's a need for expansion of high voltage direct current. There's a need for more advanced transmission technologies. In particular, a lot of the lines that were put in place in earlier times were one-way lines. So now we have to move towards a more advanced transmission system where we can more quickly deal with some of the problems that, not all of them, but a fair number of them were one-lane lines. You have to deal with more of the problems that arise in this case. And then there's a need to be focused on interregional transmission to integrate renewable energy resources. So what is the optimal dispatch problem? The optimal dispatch problem determines the most cost-effective way to meet electricity demand while adhering to operational constraints. The objective is to minimize the total cost of generation while ensuring supply meets demand. I had someone ask me when I was giving a presentation, she was like, someone asked me, why are you using this formulation? And I started giving this long rambling answer, and then someone else who is a really respected figure in my field, she stopped me and she said, no, you have an answer for this. What do ISOs do? And I started giving a long answer again. She stopped me and she said, no, ISOs do this. They do the optimal dispatch problem. And I want you to remember that. I want you to think about that when you're thinking about like how wholesale electricity prices are set. ISOs do this. This is their thing. So we talked about ISOs in the start of the class, so the lecture. This is what they're doing. So they're minimizing the cost of generation by choosing to dispatch different generators. They're balancing power. They're setting the total generation equal to demand. If we were doing this seriously, we would take out some line losses, but we're not going to worry about this with you guys. The total generation must equal total demand. There are generator limits, so the generator must be within capacity limits. You have Gmin, usually 0, and then you have Gmax, some value, and then G must be between those. Sometimes you can have that generators can't ramp down quickly, so they have to generate a certain amount in a certain time, or they can't ramp up quickly, so they can't generate more than even. So this max is not always their total capacity. And of course, this G, sometimes you can't totally control this G, like with renewables, which is why usually when people do this problem, they do net renewables, do the problem net of renewables. And then you have transmission constraints that the power flows between nodes must not exceed line capacity. So you want to minimize the cost of total generation by choosing who generates what in order to meet these constraints. You can't send much generation, you're going to lose a certain amount of generation. You have certain limits on how much each generator can generate, and it has to balance all the time. So a solution approach is formulated as a linear program or a mixed integer programming problem, depending on how you want to do it. There's plenty of IEEE literature on both. And then this is solved using automation techniques like Syntoid X or interior points. And then the real-time and day-ahead solve like this. Everyone bids in, and then you get a solution to the optimal dispatch problem. And this helps set what's called locational marginal price. So normally, the low-cost generator is the person you want to dispatch. You want to dispatch the low-cost generator first, and then LMP is a marginal cost of the last economically dispatched generator, the most expensive generator that you dispatch. So locational marginal price, LMP, is the cost of energy plus the line losses plus the cost of congestion. If there are no losses and there's no congestion, of course, meaning that you have different pricing in different places, LMP is just the cost of energy, the marginal cost of the last economically dispatched producer. So the most expensive producer gets dispatched, their marginal cost is LMP, and then plus line losses. So you have a certain amount of line losses that goes into LMP if you have to send electricity. So even if there's no congestion, electricity is not electrical prices are not always going to be the same in places because of line loss. They have to adjust for line losses. And then also there can be congestion. And this means, congestion literally means that this is an equality. So if this is an equality and you can't send more electricity, there's congestion, and the prices are going to be different across space. So with transmission constraints, if there was no transmission constraints, all prices would be equal. But with transmission constraints, some prices are higher. So here's this bidding process. You have this little generator 1 who's small but mighty, has a low marginal cost. Then you have the generator 2, a little bit larger, a little bit higher marginal cost. And then you get up to generator 4, who has reasonable marginal cost. And in region 1, generator 4 is the marginal producer and will set the price. But in region 2, generator 5 is the marginal producer and will set the price because there's congestion, because you have this flow limit. So everyone's getting dispatched, but in this region, you have a lower price. In this region, you have a higher price because demand is here. Remember, demand is vertical in electricity markets because we consider it inelastic. So demand is here, but the flow limit, the transmission line limit, is here. So the prices differ across places. I got this from NYISO. So congestion in power systems. Congestion occurs when transmission lines cannot accommodate all desired flows due to transmission capacity limits due to what are called line limits, which results in differences in electricity prices across locations. The cause of congestion: high demand in certain regions exceed local generation, insufficient transmission infrastructure, too much renewable generation in remote areas. A lot of the generation is done in places where a lot of people don't live, requiring long distance transport. And then line outages or maintenance reducing available capacity. What are the impacts of congestion? Higher electricity costs in constrained areas, inefficient dispatch of generators. You might have out of merit order generation dispatch where you have generators are dispatched before they become economical. And then, of course, you have curtailment of renewable energy generation. So what curtailment means is you're shutting off renewable energy. Renewable energy, in most models, you say, oh, well, renewable energy, God picks the generation. There's just this exogenous process by which generation is produced naturally. The sun comes up, renewable energy comes out. It's exogenous. But in reality, that's not strictly true because renewable energy generators can choose to curtail, meaning they can choose to produce nothing, or they can be told to produce nothing. And then when they're told to produce nothing, you're able to generate all this renewable electricity, but you can't, because you can't send it anywhere and you can't store it anywhere. And this is one of the bigger arguments for adding transmission lines. U.S. electricity markets face congestion costs ranging from $5 billion to $10 billion annually. This goes up and down over time. And in 2023, PJM alone reported $2.3 billion in congestion costs due to high demand and transmission constraints. I should also mention that this number is debated, and sometimes it's higher, sometimes lower, but it's a pretty significant dispersion in price. But it also has some other effects that are important, like less investment in renewables because of curtailment. And then congestion costs account for a significant portion of total electricity market expenses. So how can we fix congestion? We can invest in new transmission lines and upgrades. We can work with demand response programs to reduce peak loads or to increase loads when, to reduce peak loads. Actually, congestion would just be reducing peak loads. And then we could use energy storage to alleviate localized supply-demand imbalances so that when you have a lot of renewables, you're saving that. Or when so there's less of a need for the insurance across time. So I'll work you through some examples. Here is for how to calculate LMP. So here's LMP no constraint. There's a line limit of 100. There's a load of 90 at node B is a load of 90. The LMP at node B is 100. The LMP at node A is 100 because the generator 1 at generator A has a capacity of 150 megawatts, which is more than 90. The load is willing to purchase 90 megawatts at 20 megawatt hour, dollars per megawatt hour, which is greater than this. So this 90 megawatts is enough. It sells the entire 90 here. This generator 2, this guy who's selling at 15 doesn't sell anything. Everyone's happy. Price at A and B is equal. Everyone moves on with their lives. Now let's add some congestion. Now the load has gone up from 90 to 120. So we had a load of 90. Now we had a load that increased 30 to 120. And now this 100 from this guy is not enough. Now 100 is set, and actually you still need more. So now generator 2 comes in, saves the day with its 20 megawatts at $15 per megawatt hour. And then each is rewarded based on the local LMP. And so you have $15 per megawatt hour is the LMP at B, $10 per megawatt hour is the LMP at A. And now you have this difference in prices, which is not economically good, because now you could have dispatched A. You could have had this low-cost generation fill the entire load, because it's 150. But you had this line limit, and that, my friends, is congestion. So just a reminder, the locational marginal price is the marginal cost of the last dispatch generator at a particular location. In that case, generator 2 is the last economic dispatch generator. It's the highest marginal cost of dispatch generators, and so locational marginal price is 15 here, and even though it's 10 at A. And then the niche for renewable generation by county, to give you a sense of the scale of this problem. Notice that in these highly populated metropolitan areas in the Northeast and these highly populated metropolitan areas in New York, there's very little potential for, here we have combined technical potential in gigawatt hours per year per mile squared per mile rather. Utility scale photovoltaic, that's solar and onshore wind. And you can see there's not much potential here. Maybe there's some offshore wind potential. And then here, there's still a lot of population here, but it's not as much as like New York City. But there's still a lot of population here, but there's not as much, and there's tons and tons of generation. So the generation potential is not dispersed equally. And so the prices generally are lower here and higher here. But if you add really good transmission, you could have equalized prices everywhere. And you could have more build out of renewables in the Midwest and Texas. And then here's, right then I showed you where we see the potential for renewable build out. And here's where we see the actual renewable build out. As you can see, this is a zonal map, which means it's right below the ISO level. And we see that there's a lot of renewable build out in the center of the country. And just, they're responding to incentives, very little capacity out here. And then prices, Texas actually has relatively high prices compared to the rest of this part of the country. And that's because, it doesn't have significantly higher prices, but that's because, one, this data includes the Winter Storm Uri, which we'll talk about later in the class. That was pretty instrumental in raising ERCOT prices, but also because ERCOT doesn't have good connection, good transmission to other locations, and so there's no one who can insure it. So this is the case of bad transmission. And if you had really good transmission, you'd have relatively similar prices across everywhere. So I want you to notice, I want you to take away from this that there's a lot of renewables here, not much here. There's a lot of solar wind capacity built out here, and that has led to lower prices in this region. There's less transmission here, which explains the higher prices here. And then there's higher prices over here, very high prices where I am and where maybe you are on Long Island, because difficulty in putting transmission out here, but also limited renewables, which hopefully will be in the long term fixed by offshore wind. And then you have price differential across space and time. So once again, mention the axes, say what the graph is. Here you have price in terms of dollars per megawatt hour, and here you have hour. And you have a normal pattern throughout the day. It goes down and then it goes up. It peaks at the end of the day before going back down again, starting this back over. This is an average price per particular month. And then Yeah, the price for Long Island almost the entire day is much higher than the price in Nebraska. And then also I want you to notice, because of time zones, the price in Nebraska is slightly shifted over by about an hour. So the curve is shifted over, and also it's much lower for Nebraska than for Long Island. So this is a problem that potentially we could use transmission to fix. And we're very excited about that. One example of how we are already using transmission to fix this is our friends in Quebec, our odd French-speaking friends in Quebec have generously helped us build at what some would say is a cost that might potentially not be warranted at cost to them in some ways. Our friends in Quebec have helped us build what's called the Champlain-Hudson Power Express, which is a long-distance route that uses HVDC and then a little bit of the Astoria HVAC, but mainly HVDC, to take power from Quebec down to Queens. So here's the Astoria HVAC down in Queens. So you're generating the power in Quebec, where there's tons of hydro, and you're moving it down to New York City. And this will, hopefully in a few years, really bring down electricity prices in Queens. I was talking to a friend of mine about this recently, who works at a natural gas generator up here, and he made the point to me that, actually works at Saratoga, so he works right here. He made a point to me that, this just bypasses Saratoga, and, his generator can't compete into this. That's hard. Life's hard in Saratoga, in Albany, in the capital region. But yeah, Quebec Hydro is building this line. It'll hopefully bring down transmission costs and allow for more expansion of renewables, potentially long-term, even of more offshore wind on Long Island. I'm excited about this. I hope you're excited about this. Have a great day. I'll see you next time. Thank you.